Okay, so we're going to get started now on, I think this is problem set 9. And yeah, let's get a jump on this. So it says, if y is a differentiable function of x, and n equals y squared minus cosine of y cubed, which form of the derivative of n with respect to x is correct? Okay, well, we'll know that once we take this derivative, right? So I'm going to take the derivative of this function with respect to x. If it was with respect to y, then the derivative of y squared would just be 2y. But because it's with respect to x, we have to take the derivative. It's going to go y squared. The derivative of that's going to be 2y times the derivative of y with respect to x. Okay, because it's implicit differentiation there. So obviously we've got our sum and difference rule in action here, so we're going to take the derivative of this, which we just did. Go ahead and write that there. And then minus the derivative of this. Well, it's going to be minus, I see that there's something inside that when I take the derivative, it's not just one. So I know that I've got an inside and an outside, and I need to apply chain rule here. So my outside is cosine of something. My inside is y cubed. We know with chain rule, the derivative of that chain, I guess you could call it, is going to be the derivative of the outside of the original inside times the derivative of the inside. Right, so we see our derivative of our inside is going to be 3y squared dy dx, which means that the derivative of this right here is going to be, well, I know my outside is going to be negative sine of that first inside, so negative sine of y cubed, times the derivative of our inside, which we found was 3y squared dy dx. Okay, so we're going to subtract that down here. I'm subtracting a negative, so I'm just going to change that to a plus. Definitely be careful about that. That's a really easy way to mess up your signs, though. Oops. So just writing that all down here. And so now what we have to do is, I see I can factor out a dy dx because it's an aspect of all of my terms here. So dn dx is going to be, I know that that's going to be a 2y plus sine y cubed times 3y squared, all times dy dx. And I only factored that out and put it at the end just because that's how our forms over here have it. And we can see pretty quickly, although we don't have it exactly set up the same as this, we know that it's going to be this first option because this one has a sine and the other one has a cosine. We know that our answer uses sine. So in this case, I'm going to now take what we just found, and I do want to get it in exactly those same terms so it's easier for us to read. So we've already got this bit here. That's going to be our 2y. So dn dx equals 2y plus, and I see that they've got that leading term being this right here. So I'm just going to move that in front just so that I'm making sure that we're reading it exactly how they want us to be, so that there's no confusion. So we're just flipping these around because we can, because it's just multiplication. And it's fun like that. And then all of that is times dy dx. Okay, looks like we've got those exact terms now. So we've got an a, we've got an a times y. Our a here is going to be 2. Y to the power of b, that's obviously to the power of 1, because y to the power of 1 is just y. let's see, and then plus c is going to be 3 times y to the d. In this case, d is 2. And, oh, sorry, should be up here. And then times sine of y to the power of f, y to the power of 3. That's all that is. So let's take a look at our next one. Wow, I've got a lot of options here. So it's a similar deal. It says, given that y is a differentiable function of x, and p equals negative 3 sine of x squared times y to the 7th, what is the correct form for the derivative of p with respect to x? Okay, so we're going to go ahead and set this up. In this case, we can see pretty clearly that we've got some chain rule in here. We've also got a constant coefficient, so I'm going to go ahead and pull that constant coefficient out, because I know our answer is just going to be this times whatever the derivative of all this is. I'm going to pull that out and just kind of put that in there. And so now we just need to figure out what the derivative of this right here is. And again, we see pretty clearly that we've got an inside and an outside, so we're going to use our chain rule. In this case, our outside is going to be sine of its inside, and our inside is going to be x squared times y to the 7th. We've got to be really careful here because this requires us to use both chain rule and the product rule, right? So this is a combination of our rules here. I see that since I've got an x squared times a y to the 7th, I've got a product of these two terms. I need to use our product rule, where we know that it's the derivative, it's our first term times the derivative of the second term, plus the derivative of the first term times the second term. And I'm going to go ahead and write that out. So the derivative of all of this is going to be your first term, which is x squared, times the derivative of that second term. So the derivative of y to the 7th is going to be 7 y to the 6th dy dx. Remember, because we're taking this with respect to x, so we need to have that there. And then we don't have anything like that with our, when we take the derivative of our x, because it's with respect to x, right? So then our next part we add, it's going to be the derivative of this first part, so 2x times our second term. And because we didn't take this derivative, we're not putting any dy dx there, because that's only when we're taking the derivative of the y term. Okay, and we know the derivative of our outside is going to be, well, the derivative of our outside of the inside times the derivative of our inside. So I might need to make a little more space here. So we know that it's going to be cosine of our inside, which was x squared times y to the 7th, times the derivative of our inside, which is all of this here. So let's go ahead and write that out. And I'm just going to switch these two terms around, so don't get confused by that. So I'm going to write this one first and that one second, just because I can with addition. So it's times, and remember, put your parentheses, plus, I'm going to put the, if I've got a constant coefficient, I always want to put that in front, so I'm going to put the 7 in front there. So it's 7x squared y to the 6th dy dx. There we go. And now we've got pretty clear idea of which one it is. We haven't distributed this -3 yet, but that's okay. So I see clearly that it's not going to be this one. It's not going to be that first option. It's not going to be the second option because we know we've got a cosine. Let's go ahead and distribute out that -3, see where it gets us. So honestly, probably, yeah. So I'm going to just do, it's going to be, since it's all multiplication, then I can really just apply it to all of this, and it should be fine. So it's going to be cosine x squared minus 7th times, let's say it's going to be negative 6, because negative 3 times 2, 6 minus 21, because negative 3 times 7 is negative 21, dy dx, and there we go. Technically, I believe I could just move that negative in front there, but that's okay. I believe that should be right. I could be having a bit of a brain fart right now, but that should be right. So we're gonna go ahead and mark it as that one there, where our a, right, is gonna be that negative 6. Our b is x to the power of b. Well, it's a power of 1 right there. We just don't really write that. Then our c is this power here. D is negative 21. X to the power of f is 2. And y to the power of g is 6. All right, this one is a trickier one. It requires us to use a little bit of trig to help us out here. So it says an object pushed at an angle theta with respect to the x-axis and an initial velocity of v0 moves as this right here, this function here. So h of theta equals negative 2 over g times v0 squared times cosine of 3 theta. For this domain. And so this first part says if our initial velocity is 30 meters per second and g is, well, gravity, 9.8 meters per second squared, then the derivative of h of theta when theta is equal to pi over 3 is what? So the first thing I see here is that, well, they've given us values for these variables right here. And obviously the derivative is going to be in terms with respect to theta. So I'm going to go ahead and plug these values in for our h of theta first. So h of theta in this case is going to equal, let's see, it's going to be negative 2 over 9.8 times whatever 30 squared is times cosine of 3 theta. And we just keep doing that. So that's going to be a 900. It's going to be negative 1800 over 9.8 times cosine of 3 theta. And what this does is we don't have to worry about taking the derivative of those variables because we're plugging constants in. So we can do that initially and then take the derivative with respect to theta. So now I want to take the derivative of this here. So it's going to be h naught of theta, or h prime of theta. It's going to be, well, this is a constant coefficient, so it doesn't change. We do have a little bit of chain rule here. So I know it's going to be, that's going to be a negative sign. So I'm actually going to omit that negative because they're going to cancel out. So it's going to be 1800 over 9.8 times sine of 3 theta. And because of our chain rule, we also have to multiply by the derivative of that inside. So times 3. Or just, I could rewrite that. Oops. Could just rewrite that. Let's see, 18 times 3, 30, 24, 54. So it's going to be 5400 over 9.8 times sine of 3 theta. Okay, so this right here, I'm actually going to move it right down here so we can see it better over here. So there's our derivative right there. So we want to figure out what the derivative is at this value for theta. So we're just going to plug it in. So it says theta equals pi over 3. It's just going to be 5400 over 9.8 times sine of 3 theta, Well, 3 times pi over 3 is just pi. So that makes this 0, right? Because sine of pi is 0. If we remember our unit circle, this is pi over 2, 3 pi over 2, 2 pi, and pi. Our y value at this point is 0. It's going to be negative 1 comma 0. So this is 0. Anything times 0 is 0. So it's overall 0. Right there's our answer. And now, this is the actually tricky bit. It says determine what values of theta that the derivative of h of theta is greater than 0. Okay, so the first thing we need to do to figure that out is to figure out where our function equals 0. So we said that our derivative was, I'm going to rewrite it over here. So our derivative is, let's see, it was 5400 over 9.8 times sine of 3 theta. So we want to figure out when this function equals 0, right? So that we can then figure out on what interval that's positive and negative, right? Or greater than and less than 0. So this is going to equal 0. I know whenever this term equals 0, right? Because this is a constant, it's never going to equal 0. So it's all dependent on when sine of 3 theta equals 0. Well, I know that sine of any theta equals 0 when theta is either pi or 0, or 2 pi, or so on, right? But we only have to worry about the domain that they gave us, which is 0 to pi over 3. So, well, I know it's a 0 at pi over 3 because that's what we found already. So I know that it's equal to 0 at pi over 3. And I know if I plug in that 0, it's going to be sine of 3 times 0, or sine of 0, which is just 0. And let's think, are there any other points along there? I'll draw out our unit circle a little bit to help us. That sine of 3 theta would be equal to 0. Well, we're only going up to this pi over 3 here. And, well, if I plug in my pi over 6, that's going to be sine of pi over 2, right? Because 3 pi over 6 is pi over 2, which would be a 1, which is positive. If I plug in the pi over 4, that's going to be a 3 pi over 4, which is going to be actually over here, which is still positive for our sine value. If I plug in the pi over 3, we know it equals 0. So everywhere in this space here is greater than 0. So everything along this domain happens to be greater than 0, so lucky us. So our answer is just from 0 to pi over 3. We got really lucky that that just is our domain. And if it asks for either of this in like decimal terms rather than in like radians like that, just plug it into your calculator, pi divided by 3, and just write all of that out. Now, oh, this is a tough one. It requires us to remember a few different equations from our textbook, which I might need a moment to pull those up, actually. Let me see if I've got them written down, actually. Give me one moment. Aha, I've got them. Okay, so it says, suppose a 2-meter long light fixture falls from a 13-meter ceiling and that you are 5 feet tall and standing underneath it. So let's go ahead and draw that out, just so we've got a good understanding of what it's asking. So let's say we're in this room and there is a light right here. And I'm just going to draw it like that. the length of the light is 2 meters. The height of the ceiling is 13 meters. And I, or you, right down here, are your own 5 feet. And what you'll notice right now is that this is already, we're using 2 different units, so we're going to have to take a second to address that once we get started. All right, so it first asks us, how long do you have to move out of the way so as not to get hurt? Well, what we really need to figure that out is we need to know how much time it's going to take for this light fixture to fall before it touches us, before it hits our head, right? So it's going to be falling this distance here, which is, I'm actually going to write it like this. And that distance is going to be, well, 2 meters, 5 feet. It's going to be something in there. So makes it a little tricky for us, unfortunately, that we've got these different units. But let me go ahead and convert that. So 5 feet is the same as, what was it? It's the same as 1.524 meters. So we know that this distance right here is going to be whatever this 13 meters is, minus 2 minus 1.524, right? So we need to figure out how long it takes the light fixture to fall this distance. And the equations in our book tell us that, and I'm going to use this to describe the position. So the position, or the height of the object above the ground in meters, can be represented as this, a function of t, where time is seconds. And it's just this right here. And I know already that seems like a lot, right? But what it's important to remember is that t is time in seconds. This is distance above the ground in meters. This is the initial velocity, typically in meters per second. And this is the initial height in meters. So what we're going to figure out right here is we're going to figure out that our initial height, first of all, because that's really easy for us. Well, we know that it starts right up at the very top, except it's technically initial height is right down here at the bottom, right? Because that's what we're figuring out is what's going to hit us is this point of the light fixture. So we're going to say that its initial height is going to be 13 meters minus 2 meters. So it's going to be 11 meters high. Okay. There is no initial velocity, so our v naught equals 0. And the reason we know that is because it's just a light fixture that's hanging and suddenly begins to fall. Nobody threw it, nobody kicked it, it's just being dropped from a height, so there is no starting velocity. It starts at 0 because it was just still until it fell. And then t is what we're looking for in this case, because we're looking for how much time we have. Well, we know that the distance above the ground in meters, we want it to end up being this high, okay? So we want our S of t to equal, let me just double check that. Yeah, we want our S of t to equal our height, because that's as high as we want it to get to, or as low, I suppose, to figure out how much time passes. So our height is this right here, so I'm going to say that that's 0.254 meters. So now we've got everything except t, and we can just plug that in. So it's 1.524 is the distance it's going to get to, and I'm actually just going to make a note of that here, equals negative 4.9 times t squared plus, well, our initial velocity is 0. 0 times t is just 0. So we can actually just omit that. And then plus our initial height, which will be 11. So what we find now is we're just going to solve for t. So I'm going to, I don't actually have to write my units there. I don't know why I did that. So plus 11, I'm just going to subtract 11 from both sides. And let's see, that's going to get us 10, 9, it's going to be negative 9.476 equals negative 4.9 t squared. We're going to divide by negative 4.9 on both sides. And that's going to get us a pretty long decimal. So t squared is about, let me plug this in my calculator, this right here. And now we just, to find t, we take the square root of that. So I'm just going to use my calculator for that. So our t is about this right here. So that's how long it's going to take the light fixture to fall from this point right here that it's at, for this point to touch our head. Which means that that's how long we have to get out of the way, right? Because if we move any slower than that, it's just going to hit us. But if we move in less than this amount of time, then it's not going to hit us. We have that amount of time to get out of the way. And I'm actually going to just bring this over so I can still see it. To write it right over here. Actually, yeah, I'm just going to move that right in there. So that is, oh, let me erase the t equals bit because that's not necessary. This is our answer for that first part. It's going to take a little over a second, but a little under a second and a half to hit us. So that's how long we have to move out of the way. The next part of this question asks, how fast will the light fixture be going if it hits your head? So like if we don't move out of the way, if we just stay right where we are and the light falls, how fast will it be when it hits us? Well, that's going to be the velocity, right? So we know that the velocity of an object is the derivative of its position, right? So our position was this function. Well, let's take the derivative. Our derivative is our velocity. We're taking it with respect to t. So that's going to be negative 9.8 times t plus our initial velocity. And that's it, right? There's no t here because that would be a t to 0. So this is a constant. It gets left out. This t is a t to the 1, so it just turns into v naught. And obviously this was just more power rule. So this equation is also written in the book, but it's good to just remember that it is the derivative. So we want to know the velocity at the point that it would hit us. Well, we just found at what point it would hit us. That's when t equals this right here. And we know that our initial velocity is 0. So v of t is going to be negative 9.8 times t in this case. And if we plug our t in, so I'm going to use a calculator for this instead of writing it out. So we're just going to take that value, multiply it by negative 9.8, which tells us that, interesting, okay, that seems pretty fast. I don't know that makes sense, but alright. If I plug that in, our v of t, and I'm going to use that to just indicate that it's the t that we already found, is going to equal about this big long thing here. And that's going to be negative, of course, because it's times the negative 9.8. But the important thing to remember here is that it's asking us for the speed and not the velocity, right? So a lot of people think that velocity and speed are the same, and they kind of are, except that speed can never be negative. Speed is the absolute value of velocity. So our velocity is negative, but our speed is just going to be whatever this is, not negative. So our speed's going to be a little bit faster than like 13.5 meters per second, which seems like that's really fast. I don't know. There's a decent chance that I messed up that calculation, but I'm gonna assume that I did it right. So if you get something else, don't assume that it's because you did it wrong, but definitely like triple check work. Yeah. So then it says if instead we were 7 feet tall instead of this little 5 feet here, how much slower would its speed be when it hits you? And the reason we know that that's slower, right, is because if I'm taller, if I'm 7 feet, right, it's going to have less time to make its way down to hit me, which means that it's going to be accelerating at the speed of gravity for less time, so it doesn't get to be as fast by the point it hits me. So we're going to do everything we did before, except it changes a little bit, because the distance above the ground is no longer that 5 feet, it's going to be 7 feet. So let's figure out what 7 feet in meters is. 7 feet is about 2.1336 meters. So let's see. We know still, so that's going to be our S of t in this case. So we're going to say 2.1336 equals negative 4.9 t squared. And remember, we're solving for t again now, because we need to figure out how much time it's going to pass so that we can then figure out our new velocity, right? So we just have to start kind of all over. So let's keep going. This is the exact same as how we did it before, though. So it's going to be, I subtract 11 from both sides. It's going to be negative 8.8664 equals this. And that's going to be that our t squared equals about this long thing here. Again, you'll want to be using a calculator for this. And then you'll go ahead and take that square root. And our new t is not super far off from the other one. So it's not going to be going... I'm actually going to write this as t, like the second one, the little base of t there, just so that we can mark that this is not our original time. So we see that that is, we see that that decimal changes a little bit. It's minute, it's pretty minuscule, but it makes a big difference in our speed, technically. So now we just plug this into our velocity equation again. Remember, our velocity was this. Our v naught was 0, so I'm just going to omit that. So if we just plug that in there, then our velocity is going to equal, one moment. All right, not too big of a difference, but still different. So our new speed is that, as opposed to that right there. But it's not asking for that new speed. It's asking how much slower would its speed be when it hits you. So we need to find the difference between these. So let me move it over so I can still see it. I'm going to just bring it right over here. So I'm just going to take this right here, and subtract this, and that should be our answer. So first bit minus that second bit, and when I subtract those, and remember that this is speed, not velocity, so that's not actually negative anymore because it's the absolute value. And it's going to be this much slower. So almost half a meter per second slower, which is kind of significant, but even though it seems tiny. And that's our final answer there. I know that was a pretty tricky one. It's kind of a lot to keep track of, but I hope that that made some sense. Let's go ahead and move on to number 5. Number 5 gives us this function h of x, and then asks us to take the derivative of it, and then to take the second derivative. So let's go ahead and just take this first derivative here. So if we take that, it looks like there's only power rule involved. Lucky us, it's a nice easy one. So our h prime of x, well, I'm going to put the 4 in front. 4 times 2 is 8. 4 minus 1 is 3, so it's x to the third. Now plus, oops, got rid of my 8. And then plus, well, I'm going to put this 3 in front. 3 times 7 is 21. Times x, 3 minus 1 is 2, so x squared. So there's a minus here, so I'm going to write a minus. Put my 2 in front. 2x, 2 minus 1 is 1, so x to the first power, which is just x. And then plus, well, it's power of 1, so that just turns into 14. All right, so our a, well, we've got nothing to the power of 4, so our a is 0. We've got b times x to the third, so our b is going to be 8. C is going to be 21. D is negative 2, right, because they've got a plus sign here, and we've got a minus here. And our f is 14. And now the second derivative, to take the second derivative, we just take the derivative of our derivative. So, it won't undo. Goodness. So our second derivative, we're just going to be deriving this. It's going to be h of x. I'm going to put the 3 in front. 3 times 8 is 24 times x squared, because 3 minus 1 is 2. Now plus 2 times 21 is 42 times x to the power of 1 minus 2, and our 14 disappears because it's a constant, and the derivative of a constant is 0. I could write a plus 0, but we don't need to. So there's our second derivative. And in this case, again, we've got nothing to the power of 4, so our g is 0. Now, this time we have nothing to the power of 3, so our h is also 0. But we do have something to the power of 2, so it's j times x squared. Well, our j is going to be 24. K is going to be 42. And L is a negative 2. And that's all that is. If we were to take the third derivative, right, we would just keep going. So it would end up being 2 times 24 is 48x plus 42, and so on. Eventually, for a lot of functions, you just kind of run out of derivative, like it just ends up being 0. So if I keep going here, I eventually just get 0, and then any derivative after that is just going to be 0, right? Because there's no function anymore. But for some functions, that's not the case. Let's take a look now at number 6, though. And they want us to do the same kind of deal. We take the first derivative, take the second derivative. Our function is 2 times cotangent of 5x plus 9. So I know we're going to have to use chain rule because I've got something other than just x in here. It's a 5x. So it's going to be, let's see, our u is 2 times cotangent of something. And our, I don't know why it does that. And then our inside is going to be 5x. Well, we know that the derivative of our chain is going to be the derivative of our outside, which is just, let's see, it's 2. Derivative of cotangent is cosecant squared. And then times the derivative of our inside. Derivative of our inside in this case is just 5. So this turns into, let's see, it's 2 times 5 is going to be 10 cosecant squared of v, which was 5x. And our v prime was already multiplied. I put it in the front with the 2 to make that 10. So that's our first derivative there. So f prime of x equals 10 cosecant squared of 5 of x. So we see that our a is 10, because that's our constant coefficient. It's cosecant squared, right? Of 5 of x plus c, well, we don't have anything, so it's just a 0, right? Our c is 0. Now we're going to take our second derivative, so we're deriving this. Well, again, we have to use chain rule because we've got an inside. And we've also got its cosecant squared, so we've got 2 insides actually. So I'm going to set this up to be, our first inside is 10 times something squared. Our inside for that is going to be cosecant of something else. And then our second inside is going to be that 5x. You see how I kind of broke that down there. So the derivative of this first bit is obviously going to be 2 times 10 is 20 times v, and then times the derivative of our inside. The derivative of our first inside, since this is still a chain, we're going to take the derivative of cosecant, which is just cosecant times cotangent, and then times the derivative of our inside, and the derivative of our inside is just 5. So then plug that all back, right? So that first bit is going to be cosecant of 5x times cotangent of 5x, all times 5. And if I plug all of this back in for my v prime, that's going to be 20 times cosecant of 5x times 5 times cosecant of 5x times cotangent of 5x. And because this is all multiplying, I can definitely simplify this a little bit. I'm just going to move that 5 to be times that 20. So it becomes 100 times cosecant of 5x times cosecant of 5x, which is just cosecant squared of 5x times cotangent of 5x. And there we go. That's our next derivative. So f double prime of x, or second derivative of f of x, is going to be what we just found. Right? And then if we come back here, well, is this in the same terms as everything? Yes, it is. So our d is just 100. And then times cosecant to the power of f. You see we've got cosecant squared of 5 of x times cotangent to the power of g. Well, that's just cotangent to the power of 1, right? Because if it was 0, it just wouldn't be there. And then plus h. Well, we've got nothing, so it's just 0. Awesome. We're about halfway through, just under. Yeah, this one's pretty time consuming, unfortunately. Let's go ahead and try number 7. So in this case, we're going to use our quotient rule because we've got a quotient here with variables on both sides. Oops. So for this first bit, remember our quotient rule is, as I like to remember, low d high minus high d low over low low. So the lower term times the derivative of our higher term minus our higher term times the derivative of our lower term, all over our lower term times itself. So in this case, we're going to take our lower term, so it's 5x times the derivative of 3 times natural log of x. Well, the derivative of a natural log of x is 1 over x. So it's going to be 3 times 1 over x, which is just 3 over x. All right, so that's our low d high right there, done that. Now minus our higher term, which is 3 natural log of x, times the derivative of our lower term, which is 5, all over 5x times 5x, which is 25x squared. And now we're just going to simplify, combine like terms a little bit, I see that when I multiply this here, I'm going to have an x on top and an x on the bottom. So those are actually going to cancel, and it's just going to be 5 times 3. So it's going to be 15 minus, well, I've got 3 times 5, so 15 natural log of x over 25x squared. And I could leave it there, except they've got a 3 in that first bit, which means that we can probably simplify even more. And I see here that everything is divisible by 5. I can factor out of 5 from both my top and my bottom. So if I factor out of 5, right, that gets me 3 minus 3 natural log of x over 5 times 5x squared. Those cancel. So it just simplifies to 3 minus 3 natural log of x over 5x squared. Okay, so we've got a 3, and they've got a plus, so our a is going to be a negative 3 times natural log of x over b is 5 times x to the power of c, which is 2. Easy peasy. So I'm just going to write over here what that was, just so it's nice and clear, we don't lose it at all. And so that I can erase a little bit. Oops, didn't mean to do that. So that we've got more space. It won't erase. It won't erase. Okay. This isn't, I don't love it not doing that, but that's okay. All right, now we need to take our second derivative. So we're going to take the derivative of this, which again, take our low, d high, minus high, d low, over low, low. So we take our lower term. It's going to be 5x squared times the derivative of our higher term. So that's 3 minus 3 natural log of x. Well, I know the derivative of 3 is 0, so it turns into a 0 minus derivative of natural log of x is 1 over x. That's a 3. So that's just negative 3 over x. Okay, that's the derivative of our high there. Now, minus, there we go, minus our high d low, so our higher term is 3 minus 3 natural log of x, times the derivative of our low term, so it's going to be times 10x, all over our lower term squared, which turns into that. All right, and now once again we're gonna simplify things. So again, I see I've got an x squared on top and an x on the bottom, so I can cancel out one of those x's. So that first bit turns into a 5x times negative 3, negative 15x. Okay, right? Because if I've got 5x squared times negative 3 over x, that's the same as this. Cancel out an x. It's just 5x times negative 3, which is negative 15x. Next, we've got minus this whole thing here, so I'm going to write minus, let's see, 10x times 3 is 30x, and then we've got 10x times negative 3 natural log, and careful not to lose your negative here, it's minus this negative here, so that's going to turn into a plus, 30x natural log of x, all over 25x to the 4th. And there's definitely some like terms we can combine and further simplify. So see, I've got a negative 15x minus 30x. So I'm just going to put those together. Get negative 45x plus 30x times natural log of x over 25x to the 4th. Again, I see I can factor out a 5. And in this case, I can actually factor out a 5x because I've got an x in every term. So if I factor out a 5x, that's going to get me negative 9 plus 6 natural log of x over 5x times 5x cubed. Those cancel. And now, I'm going to bring it over here. We are left with, like I just found, this right here. So now well, good. We're in the same terms as the answer they want. So our D is going to be this -9. F times natural log of x is just 6 times natural log of x. And then over 5x to the power of g, g is 3. Okay. Let's try number 8 now. And it looks like they want us to take all the way up to the 4th derivative. So this is going to be a fun one. So we're given that h of x is equal to cosine of 4x minus 3 times sine of 4x. So I see we've got our sum rule and we've got our chain rule a couple of times. So first, our h prime of x is going to be the derivative of this minus the derivative of this. Well, the derivative of cosine of 4 of x is going to be, well, the derivative of cosine, then times the derivative of 4 of x, right? Because derivative of outside times the derivative of inside. So, the derivative of 4 of x is 4. Derivative of cosine is negative sine. So we've got one term down. And then minus, we've got same thing here. So 3 sine of 4x. 4x is our inside. So derivative of 4x is 4. 4 times 3 is 12. Derivative of sine is cosine. Bada bing, bada boom. And I'm just going to write that so that it looks a little nicer. And it looks like they want our cosine term to be listed first and then our sine term. So I'm just going to flip these around. So our h prime of x equals, flip this around, so it's going to be negative 12 cosine of 4x minus 4 sine of 4x, which makes, oh, where did my mouse go? Goodness. What? Okay, I don't know why it kept disappearing. But that makes our A, this negative 12, our B is 4, C is negative 4, and D is 4 again. Lots of 4s in that one. Ah. Goodness. Okay. Next up, why did it do that? Okay, next up, we want to take the second derivative, so we're going to take the derivative of this. And same deal, right? Little has changed, we've just got different coefficients in front of them. So, oh, I don't know why I switched from h of x to f of x's, but these should all be h's. Or I guess I could just change that h to an f and it'll all make sense. Whoopsie. My bad. So now, got our f double prime of x. Well, inside is 4 times negative 12. This is going to be negative 48 times derivative of cosine is negative sine. Bam. And 4 times 4 is 16. Again, they want cosine listed first. So we're just going to flip that around. Oops. Bam. Our f is a negative 16. G is 4. H is 48. J is 4. And just keep going down the line. It's the exact same thing that we do for all of these. Nothing changes. So it's going to be Let's see. Oh, that's tricky. What is 48 times 4? Well, 48 times 2 is 96. 180, 192. There we go. Alright, so I'm just going to move those around again. Getting into some larger numbers here. Not the most fun, but not too bad. And hopefully this is making sense. I know I'm going through this kind of quickly, but feel free to stop it, pause it, slow it down, what have you. If you need better help following these steps. But again, it's just the same exact steps for those first two problems that I did. For this, or not, for the first two parts of this problem that I did. Just repeating. And you'll notice that we do a little parentheses with a 4 in it instead of 3 dashes. You could technically write this for the fourth derivative, but once you start getting up to 4 and above, people tend to start writing it in little parentheses, just because that's a lot of little prime dashes to do. So let's see. Ooh, 192 times 4 is trickier. 400, 360, 768 times negative sine of 4x. Let's see, plus 64 times 4 to 28, 256. Cosine of 4x, flip them around again. And then do the answers. And boom, all done. Now, number 9 has some implicit differentiation going on. So we're first of all just gonna derive this implicitly, just kind of as is, so it stays in pretty much the same terms there. So if I've got x to the 3 halves minus y to the negative 3 halves equals 12, well, quite literally just taking the derivative of every term. So we want this with respect to x, because we're going to end up with a dy dx. So we use our power rule. It's going to be 3 halves times x. I subtract 1. 1 is the same as 2 over 2. So it gets me 1/2. And then we do the same thing with our y. So derivative of this, it's going to be minus a negative 3 halves. So I'm going to turn that to a plus 3 halves. Y to the, careful with your negatives here, that's a negative 3 halves minus 1. It's going to go further into the negatives. And then because this is with respect to x, it's going to be times dy dx equals, and the derivative of 12, well, it's a constant, so it's going to be 0. And that's already in the terms that they want. So our a is right here, it's 3 halves. X to the power of b, b is 1/2. C is 3 halves. Y to the power of d, d is negative 5 halves times dy dx equals f is 0. Now we're going to take what we just did and we're going to figure out what dy dx is. So all we have to do is just manipulate this a little bit so that dy dx is on one side, just as if we were solving for what y is, maybe in like our algebra topics, right? So easiest way to do this is I'm just going to make sure that we've got dy dx only on one side. So I'm just going to move my x over. I'm just going to move it over. So I'm going to subtract this from both sides. So now I've got 3 halves y to negative 5 halves times dy dx equals, and since I subtracted this, it's now negative x to the 1/2. All right, and since this is multiplication going on here, if I want to get dy dx by itself, I just have to divide both sides by this. So that's going to get me that dy dx equals, since I'm dividing both sides by this, it's going to cancel on this side, and it's going to be what we have already divided by this right here. So 3 halves y to the negative 5 halves. And clearly that's not in the terms we wanted in yet. So we're going to have to do some rearranging, simplify it. Well, if I've got 3 halves divided by 3 halves, I know that's going to cancel just outright. So I know I'm just going to have negative x to the 1/2 over y to the negative 5/2. And easiest way to fix this is just with our exponent rules. What? Why did it erase my y? Of all the things. Let's just use our exponent rules. So this is going to be negative x to the 1/2 times y to the positive 5/2, right? Because if it's negative, it's on the wrong side of the fraction line, is how I like to think about it. So we just found dy dx equals negative x to the 1/2 times y to the 5/2. Is that in the terms they wanted in? Looks like it. G is going to be a -1. H is 1/2. And J is 5/2. Boom. All done. Let's try number 10. Number 10 is similar, but it's a little bit more complicated to work with. Sorry. Got a scratchy throat. So again, we're going to figure out what dy dx is. So we're going to just implicitly divide with respect to x. Or differentiate. So I know that the derivative of a natural log of x is going to be 1 over x. So what I see here is that I've got two terms in there. Well, so it's going to be because this is a 3y, I know we're going to have chain rule involved. Sorry, I'm a little tired. Took me a second. I know we've got chain rule involved because we've got this whole inside. So I know in this case, I'm just going to write that up there. So our u is 2 times the natural log of something. And our inside is x plus 3y. Well, I know the derivative of our u, of our outside, is going to be 2 times the derivative of our inside over the inside, right? Or I could rewrite that. I could just do this times that, but I like to just put that on top because it's easier for me to read personally. And then the derivative of our inside, well, x is 1. And the derivative of 3y is 3 times dy dx. So the derivative of this whole thing right here is going to be 2 times 1 plus 3 dy dx over our v was x plus 3y. And then we have to take the derivative of our other side, which is x to the third, so it's going to be 3x squared. All right, now we're just going to distribute that 2, just so that it's a little better to work with. So we're going to get 2 plus 6 dy dx over x plus 3y equals 3x squared. Okay, well, I want my dy dx to be the only term, so I'm going to work backwards, just some algebra here. Going to multiply both sides by this so that it cancels out. So it's going to get 2 plus 6 dy dx equals 3x squared times that bottom term there. So, bam. And now I'll just subtract 2, because again, all we're doing right now is we're effectively solving for a variable, except our variable in this case is just dy dx. And I'm actually going to distribute this. So it's going to be 3x cubed plus 9x squared y, and then we just subtracted a 2. Okay. And now all that's left to get my dy dx alone is to divide by 6. So dy dx equals 3x cubed plus 9x squared y minus 2 all over 6. And obviously we don't have to, but I would recommend simplifying fully. And I see that, oh, maybe not. Never mind. This is it. I really thought that there was, yeah, this works. So let's go ahead now. We see that our a is 3, x to the power of b, it's also 3, c is 9, x to the power of d, d is 2, y to the power of f, f is 1, plus g, we've got a minus 2 here, so our g is negative 2, and then all over h, h is 6. All right, just 3 more questions, I think. We've got 11, 12, and 13. Yep. Okay. So let's take a look at number 11. It says if we have this here, so 2 times e to the 3xy equals 3y minus 7x plus 2, use implicit differentiation to find dy dx. This is kind of just like the other one, except, again, a little more complicated. We're going to have 2 terms for dy dx, I believe. So it's just going to be a little bit more manipulating our equation to get something that we want. So remember that the derivative of e to the x is just itself. But since we've got other terms in here, rather than just e to the x, we've got 3xy. So we know we're going to use chain rule with our outside being the e to the something and our inside being that 3xy. So 2e to the v is 3xy, and I want us to be really careful here. So we know we're going to have the derivative of this is going to be the derivative of our inside times the derivative of our outside, which is just that. But the derivative of our inside, that's an x times a y, which means we have to use our product rule. So I'm going to do 3 times all of that. So it's going to be 3 times x times the derivative of y, which is going to be dy dx, plus 3 times the derivative of x is 1 times y, which means the derivative of this right here is going to be, oops, it won't go away. It's going to be, let's see, it's going to be 3x dy dx plus 3y times 2e to 3xy. Okay, and that's one of our sides down. And now we just have to take the derivative of this side with respect to x. So the derivative of 3y is going to be 3, and since it's y, it's going to be dy dx minus, well, 7. And then our plus 2 disappears. It turns into a 0 because the derivative of a constant is 0. So now we've got a little bit of trickiness going on here. So again, just so that I can work with this, I'm going to distribute my e term. So it's going to be 6 x times e to the 3xy times dy dx plus 6y times e to the 3xy equals 3 dy dx minus 7. And again, we're trying to get dy dx all by itself, but the first thing we have to do before that is to get all of our dy dx terms on the same side. So, and everything that isn't those terms off it. So I'm going to go ahead and move this over by subtracting it. So I'm going to get 6x times e to the 3xy times dy dx. I'm subtracting this, so I'm just going to go minus 3 dy dx, and we still got that right there, so plus 6y e 3xy equals negative 7. This doesn't have a dy dx term, so I'm going to move it over to our other side. It keeps lagging. I don't love that. So 6x e to the 3xy dy dx, oh, that was sloppy, minus 3 dy dx equals negative 7 minus 6y times e to the 3xy. All right, we're making progress. Now, on this side, both of my terms have a dy dx in them, so I can factor that out. So dy dx times this bit here, so 6x e to the 3xy, and minus 3 equals this over here. And now to get my dy dx alone, I just have to divide everything by this here. So I'm going to write that over here. Dy dx equals negative 7 minus 6 times y times e to the 3xy over 6xe, so 3xy minus 3. And it's not quite in the exact terms that they wanted in. I'm just going to move this around so that my negative 7's at the end. So I'm just going to rewrite that bit there. If my computer will let me. I don't know why it lags so much with this. Yeah, so it's a negative 6y times e to the 3xy minus 7. And I just moved this around so that my negative 7's at the end. And now it's in terms that we want it to be in, just like that. So we see our a is going to be negative 6. Our x to the power of b, well, we don't have an x, which means that it has to be x to the power of 0, because that's going to equal 1. So b is 0. We've got a y to the power of 1. E to the power of 3xy plus f. Our f has to be negative 7. That's why I moved that around. And then on the bottom, our g is going to be also 6. And we do have an x this time, so it's x to the power of 1. We don't have a y, so our y exponent has to be 0. For the same reason, it's going to equal 1. So j is 0. And then e to the power of kxy, so it's 3 minus 3, so plus l. L is negative 3. Now just 2 more questions. Number 12 is a nice quick one. So it says if 4xy equals 7, when x equals 2, y equals what? Well, let's just plug that in. So 4 times 2 times y equals 7. That's going to be 8y equals 7. Y equals 7/8 when x equals 2. Ta-da! And now, also when x equals 2, our dy dx equals what? Well, let's go ahead and derive this. So this is some implicit derivative here. It's lagging again. Sorry. I hope it's recording okay if it's lagging that much. Right. So we're going to take that derivative. So again, we need to use our product rule because that's an x times a y. That's a product of x and y. So it's going to be 4x times the derivative of y is dy dx plus 4y, because the derivative of x is 1, minus y, equals, well, the derivative of 7 is 0. So now I move my terms around, so I just got all my my dy dx is on one side, and then I divide that out, so it's just the dy dx on that side, and obviously the 4's cancel, so it's just negative y over x. So our dy dx, we just found, equals negative y over x, but we want to know what dy dx equals when x equals 2. Well, when x equals 2, x is 2, so it's going to be negative y over 2, and y equals 7/8. So we're going to plug that in, so it's going to be negative 7/8 over 2, which is just negative 7/16, I believe. And that is our answer. And now our very last question, which is a bit of a tricky one. They kind of all are, but yeah, so we're given this equation here, and we want to derive it implicitly to figure out what dy dx is. So let's go ahead and do that, figure out what dy dx is. Well, the derivative of 3x is going to be, of x to the third is 3x squared. Derivative of 3y squared is going to be 6y dy dx equals the derivative of 75x is 75. Okay. And again, I'm just going to move terms around to get dy dx on its own. You'll see right here I'm just subtracting 3x squared from both sides for that. And then we're going to divide out that 6y for the same reason. And here, I could just leave it like this, but I am going to simplify this. I can see that I can factor out a 3 from all of that. So 3 times 25, it's going to be 25 minus x squared over 2y. Yeah, I just factored a 3 out of my top and my bottom, and they canceled out. So we just said our dy dx equals 25 minus x squared over 2y. Okay, so our a is 25, our b is a 1, because it's just minus 1 times x squared, so c is 2, and our d is also 2, because it's 2 times y. Now the trickier bit is using that, we want to find the equation of the line tangent to this equation up here at this point that they're given there. So 3 comma 8.124. So we know that there's several different ways that we can write an equation of a line. Typically we want to go with either point slope form or slope intercept form. In this case, I'm just going to use point slope form because that's honestly easier to work with. Point slope form is the whole this right here kind of deal. Oops. Well, we just found our slope. Our slope is our derivative, so it's dy dx. So we want the slope at the point is going to be just this when we plug in the x and y. So let's see, if I plug in an x, that's going to be 3 squared, so it's 25 minus 9 over 2 times this right here, which is going to be 16.248. And I'm just going to do that right up there, 248. I believe that's right. So I'm going to leave it in that fractional term right there, even though we don't like fractions with decimals in them. But I'm just going to leave it like that so it's easier to read. So it's going to be y minus our y term, which is this right here, equals our slope. Feel free to use a calculator for this part. I recommend it for the actual homework, but I'm just doing this for time's sake. So it's our slope times x minus our x value, and boom. That's all there is to it. And I think, yeah, that was our last question for this one. So we are all done. This is all done. And I know this was a pretty time-consuming one. I hope that everything, or at least mostly everything I went over made sense. I know I'm a little tired today, so I didn't do a great job of explaining some of it. But I hope that this was helpful. And yeah, thank you for watching.